Hey everyone, this is the warm-ups for lesson 3 of unit 4 in our calculus curriculum. So let's go ahead and get started with these warm-ups and then we'll dive into the lesson in the next video. So number 1, it's asking to identify all the extreme values, or at least where they occur. In other words, what are the x values where f has a relative extrema? So let's go ahead and take a look at what it gave us. Number 1, it said that f prime of x is equal to x minus 1 times x plus 1 squared times x plus 2. So last lesson we talked about the idea of critical points. Critical points identified places where extrema may occur. So critical points occur, if we remember, when f prime is equal to 0, when f prime does not exist, and at endpoints. So we need to identify the critical points of this function first. Well, notice that we were given f prime. So we don't have to take the derivative, it's already given to us. We just have to identify the critical points as a step 1. So let's find out the first thing where the derivative is equal to 0. So we're going to set this function equal to 0 here. So 0 equals x minus 1 times x plus 1 squared times x plus 2. And yes, this is an essential step or an essential line that you're going to want to write down in terms of when the AP readers are looking at giving you credit. Because they want to see that you knew that f prime equals 0. So from here we're going to say this is true when x equals 1, when x equals negative 1, and when x equals negative 2. So these are all critical points of our f function because f prime is equal to 0. So let me go ahead and write those down. Critical points are x equals, I'll put them in order here, negative 2, negative 1, and 1. So now we have to ask ourselves, do we have any other critical points? Well, the second type of critical point, the second place where we get critical points is when f prime does not exist. Now you'll notice here, f prime is actually a polynomial function. So polynomials exist everywhere. Their domain is all real numbers. So therefore, f prime exists everywhere. So f prime, there is no place where f prime does not exist. So those types of critical points don't exist in this one. And then our third type of critical points are at endpoints. Well, in this problem, it didn't give us any scenario. So it didn't give us an interval to look at. If it gave us an interval, then those two endpoints of that interval would also be critical points. So in this case, we only have 3 critical points. So now from here, what we're going to do is we're going to draw a number line that represents our x-axis here, and we know that we have a critical point at negative 2, one at negative 1, and one at 1. And so this is when the derivative, I'll use a slightly different color here, the derivative of f prime, is equal to 0 at these 3 points. Now, in order to identify where extrema, relative extrema, occur, we have to understand that for us to get a maximum or a minimum of any kind, that means that the function is the highest within that small window. So if that's the case, we can simply understand it this way. If the function is going up and then it goes down, that's going to be a relative maximum. Or if it goes down and then it goes up, that's going to be a relative minimum. The bottom line is, if the function is increasing and then decreasing, or decreasing and then increasing, we have to see a change in the signs of f prime. So we want to observe f prime changing signs. Well, f prime can only change signs at these 3 points, but that doesn't guarantee that it does change signs at those 3 points. So we have to check the signs of f prime within these 4 intervals here. And the way we did that is we plugged in values that are less than negative 2 to our f prime function here. So if I plug in, let's say, negative 3 into our f prime function, if I plug in negative 3 here, I'll just put a little notation here. Negative 3 minus 1 is a negative. Negative 3 plus 1 is a negative, and then we're squaring it. And then negative 3 plus 2 is also a negative. Negative 3 plus 2, sorry, yeah, that's right, okay. So negative 3 minus 1, negative 3 plus 1, negative 3 plus 2. And then if we simplify all this, well, we got a negative squared, that's a positive. So we have a negative times a positive times a negative. That's going to end up being positive right there, okay? So now we're going to plug in values. Now we're going to plug in values in between negative 2 and negative 1. So maybe we'll plug in negative 1.5. Well, if I plug in negative 1.5 here, I'm going to end up with a negative. If I plug in negative 1.5 there, I'm going to end up with a negative, and I'm going to square it. And if I plug in a negative 1.5 here, negative 1.5 here, I'm going to end up with a positive value. So if we simplify these values, whatever those numbers are, it doesn't really matter. We only care about the signs here. A negative times this will be a positive times a positive ends up being negative. Okay? And now we'll check our next region within negative 1 to 1. So a nice value to use there is 0. So if I plug in 0 here, we'll end up with a negative. We'll end up with a positive squared, and we'll end up with a positive. So ultimately, this turns into a positive value. And then the last place we need to check is greater than 1. So we're going to plug in a value, an x value greater than 1, so we'll plug in 2. So we end up with a positive here. We'll end up with a positive squared there, and we'll end up with a positive there. So all of that multiplied out ends up being positive values. Well, what that does for us is it tells us the direction of f. If f prime is positive, f is increasing. So we're going to just draw a little arrow pointing up. And if f prime is negative, f is decreasing. If f prime is positive, we have increasing and then increasing again. So we can see, observing here, that we have a change in direction of our function at x equals negative 2 and x equals negative 1. So we can conclude here that f has a relative maximum when x equals negative 2, okay? And we're going to justify this. We want to justify this guy. F has a relative maximum when x equals negative 2 since f prime is changing signs from positive to negative. All right, so now we've identified where a relative maximum occurs. It occurs at negative 2. At negative 1, we see that f prime is changing from negative to positive, which means that f is changing from decreasing to increasing. So we can then conclude that f has a relative minimum when x equals negative 1, and the justification for that is since f prime is changing signs from negative to positive. Okay, and then if we look at our other critical point here at x equals 1, f prime is positive and then it's positive again, which means f is increasing and then increasing. So what this kind of looks like at this point is that we have a function that's going uphill and then it flattens out because the derivative is 0, and then it goes uphill again. So at this point, at x equals 1, it is not the highest point within a very small window around it. We have points that are lower than it, but we also have points that are higher than it. So it's not a relative maximum, and it's not a relative minimum either. So if we want to make another conclusion here, we can say f does not have a relative extrema at x equals 1, since f prime does not change signs. Okay? So again, for f to have a relative extrema, f prime has to change signs from one to another either way. This is a huge part, especially the justification, this is a huge part of getting a good score on the AP exam. Okay, for number 2, we're looking for the slope of the tangent line of this equation 2y cubed plus 3xy equals 4x minus 6. So let me go ahead and write that down here. We got 2y cubed plus 3xy equals 4x minus 6. So this is not a function. This is an equation that relates x and y. So we're going to get some sort of graph that's not a function, basically. And we're looking for the slope of the tangent line of this graph at a specific point. So I don't know what this graph looks like, but it might look something like this, where it comes back on itself or something, right? And at the point when x equals -1, let's say we're on this graph here, and this is -1 here. Well, we have an x value, or sorry, a point at x equals -1 here, here, and here. So that's why it gave us both points. It said -1 and -2 for the y value, because that tells us which of those 3 points we're going to be looking at. So in order to find the slope of a tangent line, we have to find the derivative of our equation and then plug in the point that the point of tangency. So when I take this derivative, I want to note that the derivative is actually going to be written as dy over dx ultimately. What that does for me is that it tells me that x is my input value and y is my output. So I'm taking the derivative in respect to x. And so when I take the derivative of y in respect to x, like here or here, we have to apply the chain rule for that. So let's go ahead and take this derivative here. The derivative of 2y cubed, we're going to apply the power rule, so that's going to be 6y squared. But then we have to remember that y is in respect to x. So I said it's not a function, but if we think of it as a function, y is a function of x. So therefore, y has to apply the chain rule. Y is the inside thing. So the derivative of y here then is y prime. Now we can use that notation y prime, but I actually like using dy dx as the notation. It just helps us understand calculus in a better way. So the derivative of 2y cubed is 6y squared times dy dx. For the second part, we have the derivative of 3xy. Well, here we want to recognize this as a product, and there's a couple different ways of doing this. I prefer sticking the constant with one of these things, so I'm going to say that the first equation that I have is 3x, and the second one that I have is y. So we're going to use the product rule for this. The derivative of 3x is just 3 times the second thing, so times y. Remember, it's the derivative of the first thing times the second thing plus the derivative of the second thing times the first thing. So the derivative of y now, again, is dy dx times the first thing, so times 3x. So now I've got the derivative of the left-hand side. Because I took the derivative of the left-hand side, I've got to do the derivative of the right-hand side. So the derivative of 4x is just 4, and the derivative of -6 is just 0. So this is my equation that relates x, y, and y prime all together. Now, normally I would say let's isolate dy dx and then plug in our point that we're concerned with. But it's only asking for the slope of the tangent line at a specific point. So it would be totally okay for us to just take that point, -1, -2, and plug it in now, knowing that we are evaluating dy dx when x equals -1 and y equals -2. So just keeping that in mind, that we're not finding a function or an equation for the derivative at this point. We're finding the slope of the tangent line when we plug these points in. So let's go ahead and plug that in now. We end up with 6 times y squared, so that's -2 squared, times dy dx plus 3 times -2 plus dy dx times 3 times the x value is -1, and that's equal to 4. So now I have this equation that I can solve for dy dx. And again, the reason I do it this way is because I could solve for dy dx, but what I find is that students tend to have a harder time isolating dy dx here because of all the extra variables, where here we have numbers, so it's just easier to isolate dy dx this way. And we can do that because we're looking at a specific point. So simplifying this, we got -2 squared is 4 times 6 is 24, and then times dy dx. And then we've got a -6 here, so -6. Here, 3 times -1 is -3, so it's -3 times dy dx equals 4. And then we'll solve this, so we end up with 21 times dy dx equals, we'll add the 6 to both sides, we get 10. And therefore dy dx equals 10 over 21 when x equals -1 and y equals -2. So we'd say the slope of the tangent line is 10 over 21. So stick around for the lesson on 4.3, determining extreme values.